One task required in most high school chemistry classes is the ability to convert quantities both within the metric system and between the metric and the English systems of measurement. So our first, and I think the more important goal today, will be to get very good at converting between units within the metric system. There are a few ways to accomplish this. We're going to discuss two. One popular way is to use the factor label approach. Another way is to use a technique that I like to call the big guy, little guy method. Consider this conversion. Convert 4.38 centimeters to meters. Let's first do this conversion by using the factor label approach. In this case, you start with 4.38 centimeters, and you need to convert this into units of meters. To convert centimeters into meters, you're going to need to multiply it by a factor that has centimeters in the denominator, so this unit will cancel out, and that has meters in the numerator, so our final answer will have units of meters. There are actually two different ways this factor can be written. It can be written as 1 meter per 100 or 10 to the second centimeters, or 1/100th or 10 to the minus second meters per 1 centimeter. You then do the arithmetic and you obtain an answer of 0.0438 meters. That's fine. But I'd like to show you another approach that I have dubbed, as I said, the big guy, little guy method. Big guy, little guy, I mean, what is that supposed to mean? Let me show you by working this problem. You're supposed to convert centimeters into meters. Think about these two units. A meter in this problem is a big guy. Me meter, me big guy. A centimeter in this problem is a little guy. Me centimeter, me just a little guy. Meter, big guy. Centimeter, little guy. Now, in order to do this conversion, I only need to know two things. The first is, how many places should I move the decimal point? Well, since centi is 10 to the minus second, and the meter is a base unit, which means its magnitude is represented by 10 to the 0, as was explained in the last lecture, these two quantities differ from each other by 2 powers of 10. So I know that I'll have to move the decimal point 2 places. But the real question is which way? To the right or to the left? Here's where the big guy, little guy thing comes into play. In this problem, a meter is a big guy. Now, when something is big, do you have a lot of them or not very many of them? Now, I don't mean this literally. I mean, stars are big, and we certainly have a lot of them. But think of it this way. Have you ever seen as many elephants in one place as you've seen ants or bees? I doubt it. So we're going to assume that if something is big, you don't have many of them, like elephants. But if something is small, you get a lot of them, like ants. So if you're converting to a big guy, you're not going to get very many of them. So you've got to have fewer meters than centimeters. That tells me that my answer is going to be smaller than 4.38. And I've already determined that I have to move the decimal point 2 places. So to get a smaller answer, I know that I have to move the decimal point to the left. Moving the decimal point 2 places to the left gives me the correct answer of 0.0438 meters. Okay, let's try another one. Convert 8.86 centimeters to millimeters. Centi means 10 to the minus second. Milli means 10 to the minus third. I think you can see that you're going to want to learn these prefixes as quickly as possible. The difference between 10 to the minus second and 10 to the minus third is 1 power of 10. So I'm going to move the decimal point 1 place. Millimeter is a little guy. A millimeter is smaller than a centimeter. If it's a little guy, I'm going to get more of them. To get more of them, I've got to move the decimal point to the right. So I'm going to have more millimeters than centimeters by 1 power of 10, or 1 decimal place, which means that 8.86 centimeters is equal to 88.6 millimeters. Let's try another one. Convert 1.35 millimeters to kilometers. Milli means 10 to the minus third. Kilo means 10 to the plus third. Now, how many powers of 10 do you need to go from 10 to the minus third up to 10 to the plus third? 6. That means that I'm going to have to move the decimal point 6 places. That's kind of a lot, but that's what I'm going to have to do. Is the kilometer a big guy or a little guy? Well, here he's a big guy. I mean, a very big guy when compared to a millimeter. So I'm not going to get very many kilometers. To get fewer of them, I'm going to have to move the decimal point 6 places to the left. Wow, that is really putting a lot of zeros in my answer. Too many zeros, frankly. I mean, a much better thing to do would be to multiply the 1.35 by 6 powers of 10, which would then put the answer in scientific notation. Of course, now I have to decide whether to multiply it by 10 to the 6th or 10 to the minus 6th. How do I decide that? Well, since I know that I need to get a smaller number of kilometers than I had millimeters, this tells me that I should multiply by 10 to the minus 6th, not 10 to the 6th. Let's try 2 more to be solved together. Convert 5.33 millimeters to nanometers and 5.33 times 10 to the 4th millimeters to gigameters. These 2 problems were presented together to illustrate the fact that something can be a big guy in one problem but a little guy in the next. In the first problem, milli is 10 to the minus third, nano is 10 to the minus ninth. 10 to the minus ninth is smaller than 10 to the minus third by 6 powers of 10. So in the first problem, I must multiply 5.33 by either 10 to the 6th or 10 to the minus 6th. Milli is a big guy in this problem. And since nano is a little guy, I know that I am going to get a lot of them. This tells me that I have to multiply by 10 to the 6th. So my final answer is just 5.33 times 10 to the 6th nanometers. In the second problem, milli is a little guy and giga is a big guy. Milli is 10 to the minus third. Giga is 10 to the 9th. These differ by 12 powers of 10, not 9. To go from an exponent of minus 3 to an exponent of plus 9 is a difference of 12 powers of 10. So I have to multiply by either 10 to the 12th or 10 to the minus 12th. And since giga is a big guy, I know I don't get very many of them. So I multiply by 10 to the minus 12th. Now you have to watch your exponents. I have to multiply 5.33 times 10 to the 4th by 10 to the minus 12th. In math, we learn that when we multiply exponential numbers, we just add the exponents. So 10 to the 4th times 10 to the minus 12th is just going to be equal to 10 to the minus 8. Our final answer is 5.33 times 10 to the minus 8th gigameters. Now, we could undoubtedly spend a lot more time practicing these kinds of problems, but I'm not sure it would be time well spent when compared to other things that we need to discuss. So if you need additional assistance and practice on these, you can probably find them in your textbook, and I've included several of them in the workbook that accompanies this course. So let's move on. Another kind of problem that chemistry students are typically required to solve involves converting a measurement from one system of measurement to another, typically from the English system to the metric system or vice versa. The most popular way to accomplish this is to apply the factor label method. Now, I've previously mentioned that this is the most popular approach to solving most introductory chemistry problems because you can usually obtain the correct answer without having to have any understanding whatsoever about what the numbers in the problem actually represent or what the problem is really talking about. This, of course, is its great strength, but in my opinion, also its great weakness, if you really want to learn and understand something about chemistry. That's why I've been recommending that you do not rely on using this approach. If you want to understand, really understand a concept, then I believe that blindly applying a factor label approach may make it much less likely that you will. But if you are not concerned about learning the concept, then I think it's a fine approach. But when would you not be interested in understanding a concept? Well, how about when all you're trying to do and all you're trying to accomplish is to convert one set of units into another? That, of course, is exactly what the factor label approach is designed to do. So if converting units is your only goal, then it seems to me that this would be a very appropriate approach. So let's take a look at how we can apply factor label to solving problems involving these types of conversions. Let's look at a sample problem. Convert 53.9 inches to centimeters. Now, you might want to do this, for example, if you were trying to send some plans for a building, a doghouse, to a friend of yours who lives in Europe. In order to do that conversion, the first thing you need to know is what's the relationship between inches and centimeters. Now, there's no way you can figure this out. You just have to know it. Look it up, or it's going to be given to you in the problem. This relationship happens to be 1 inch equals 2.54 centimeters. If you think about this, you realize that an inch is bigger than a centimeter. In fact, it's a little over 2.5 centimeters. 1 inch equals 2.54 centimeters. This relationship can be expressed two different ways. And this is critical to becoming good with this method. I can either say that there are 2.54 centimeters per inch, or I can say that there is 1 inch per 2.54 centimeters. And I'd like to make one small comment here. I've always found it interesting to consider the notion that two students can look at the same mathematical statement but think about it differently, depending on what approach they are using to solve a problem. When we are using what we've called logical thinking and we see a quotient like 1 inch over 2.54 centimeters, we think of this as telling us how many inches there are in 1 centimeter, in this case less than 1 inch. But when we are just analyzing units, we only think of this as stating the relationship between the inch and the centimeter. In this problem, I am starting out with 53.9 inches, and I want my final answer to come out in centimeters. So how could I do that? Well, what I need to do is multiply the 53.9 inches by a factor. And that factor has to have the correct labels. This means that I need a factor that has inches in the denominator, so inches will cancel out, and has centimeters in the numerator, so our final answer will come out in centimeters. That factor, of course, is 2.54 centimeters over 1 inch. The units work out correctly, so now I just do the math and obtain my answer of about 137 centimeters. When you solve these kinds of problems using the factor label approach, there are a couple of things that you have to watch out for. One, be sure to get the factor set up correctly so that the units cancel out the way they should to produce the correct units on the answer. For example, in this problem, inches had to be in the denominator of my factor, so they would cancel out the inches in the numerator of the other factor. It's pretty easy to set these factors up upside down. It happens all the time. Secondly, the other thing you have to be careful about is to be sure to put the number in the right spot. There is a tendency to always want to put the number other than 1 in the numerator. In this problem, that's 2.54, and in fact, it does go in the numerator. But in a different problem, the factor might be 1 over 2.54. Be careful about this. With these two ideas in mind, let's try a few more problems.